Thank you for joining. Harish, take it away.
Hello, everyone. Myself, I'm Harish. I'm doing PhD in natural language processing at Stevens Institute of Technology. Um, I research in fact verification and evidence extraction. That's the area of my research. But I also I deal with prompt engineering and optimization techniques. Um, so today I'm going to present some of the useful techniques that are not actually used in not widely used in the major companies right now, or in the technical world right now. Prompt engineering is bigger than RAG models. I know everyone is only talking about RAG in terms of optimizing LLMs, but it's beyond that. It's I just want to share my knowledge with the community. So let's get started. um, so these are the topics I'm going to discuss today. I'm just go over the slide. Okay, introduction. So I know everyone thinks LLMs are actually smart enough to perform almost anything, including mathematical operations, writing stories to TV shows, and writing emails for you, and maybe writing research papers too. But are they actually smart enough? Can they actually perform every task, and what makes LLMs so smart? Why are everyone talks about ChatGPT? Yes, that's actually a very industrial friendly model, and also it's a very good performing model. But it's ChatGPT is not the only large language model. There are other large language models like Llama, Mistral. What are those? Why aren't we using those? It's because BERT too. I don't know, how many of you heard about BERT, SciBERT, and BioBERT models. So LLMs actually differ based on the kind of data they are trained on, and the architectures they use for this training. That's a huge difference there. And some of the LLMs, they're actually hosted by the company's servers, which actually have high performing GPUs and really large memory spaces. And some companies don't. They actually freely open source their large language models. As long as you have the hardware, you can use it. So that's why most of the people are inclined towards large language models which have servers, and not usually explore the other kind of large language models. So I'm going to start with the LLM's brief history. For just a vague understanding, non-technical understanding about what some of the basics of LLMs actually started with attention mechanisms. Attention mechanism is basically every word in English, if you take it as an entity, you give it a personification, like how this word favors and not favors other words in English, and how they are presented in different contexts. If you combine them with different sentences, this is a word vector space. Imagine a three-dimensional figure, and every point it's like a multi-dimensional figure, but every point has its uh, own vector space where it actually says okay, I favor you this much, I don't favor you this much. So attention mechanisms are trained based on self attention or cross attention. Self attention is large language models are actually evolved on three different tasks. Very primitive large language models, masked training, where you actually take one word off and make the large language model guess it, if you're guessing it right or wrong. The more you train it, actually it gets better at guessing those words. So it actually creates a pseudo language, like a pseudo universal language, which is zeros and ones in the background, which is not different, which is very different from the languages we use in our communication. And self attention is where you're actually training using the same inside the same sentence, how different words are favoring each other. And cross attention is you're putting two sentences together and actually saying this sentence is actually like, favoring this sentence, and this sentence is opposing this sentence. Like, you can say like, maybe you can use the same sentence in like different contexts, like, how you say like, oh my God, and it's like, in a happy way, and oh my God, and like in a very anxiety way. Like how that's like, that actually depends on the context. And like, cross addiction, you are actually training like, that level of understanding for the large language models. And LSTMs are different than transformers. LSTMs is almost like a bygone age model, but like, I'm not going to go too deep into that. It's basically like, it takes every word in, and it actually like, it processes each and every word, like, word by word. It's actually a time taking and like, computation exhaustive process. And it doesn't actually maintain like long-term memory. So people moved on to transformers. Attention is all you need is the first paper that actually mentioned and introduced transformers in 2017. So that's actually the like foundation stone for almost all large language models right now. And in GPT 3.5, the prompt engineering was actually introduced, which actually opened up large language models not just to research community. It actually opened up to almost everyone who can understand a language. So prompt engine, before going to prompt engineering, I want to say like, prompt engineering is a very important tool. Probably everyone will need to understand and need to know at some point in future, because how fast AI is taking over, and you may not know you're already using AI models every day in your life, one way or the other. Like your phone is all full of it, and your emails are like prompt engineering, like, knowing to learn how to interact with large language models and like, get things done, it will be a necessary skill at some point. And our large language models these days are actually trained on hundreds of billions of parameters. That's where they're evolving it. Parameters are vector space. In a way, like, how our human eye can actually see like people in front of us, but it cannot see like, skin cells underneath. That actually depends on like, how much we are magnifying it. And you can actually understand like, the parameters actually are the magnifying spectrum of it. The higher the number of parameters, the more deeply you can actually analyze the language and a language space, and you can understand intricate relations between it. So that's how like large language models get perfect. So hallucinations is one thing like which large language models actively suffer with. But what are hallucinations? The first statement I give here is actually a medical definition of hallucination in human brains. It's not very different from hallucinations what large language models suffer with. It's strongly overly precise priors can give rise to the perceptions in the absence of stimuli. So strongly overly precise priors, it's actually the knowledge what we learn prior to like, the current existence, the current state of existence. Large language models these days are trained on huge amounts of data, like terabytes and terabytes of like thousands of terabytes of like, live data, like all that's available online. And you may have heard about like, phrase like, too much knowledge is actually not a very good thing. So large language models actually kind of suffer with that. So in the like, just few slides before I actually explain like, what attention mechanisms are. And what happens with this huge data training is like, it gets overtrained. You may actually want to use, you may not need that amount of knowledge. You may need like, a simple task like how to make a coffee. You don't need to like, go to Ghana and like, buy some coffee beans from there and like, make some coffee by yourself. So that's where like simple tasks differ from like, complex knowledge. And so if you are asking like, large language models, you want it to stick to certain context. If you actually wanted to use large language models for designated tasks, You don't want to go beyond the scope of your use case, but large language models go beyond that use case or get it confused. That's where large language models suffer with. There are two types of hallucinations large language models suffer with. It's intrinsic hallucinations and extrinsic hallucinations. Intrinsic hallucinations are large language models confusing, the internal data, whatever you're giving it. Within the scope of the data you're operating it can sometimes misinterpret the information you're trying to teach it. And extrinsic hallucinations is, oh, sorry, I got the spelling wrong. So extrinsic hallucinations is where the large language models are trying to use their pre-trained data to kind of mess around with the solutions. Sometimes you don't want a large language model to already come up with solutions. You want it to problem solving part, but you don't want the solutions, but they actually give you their own versions of solutions. So that's extrinsic type of hallucinations. I will give you more examples how they work in the live performance one, live testing code I wrote. So the to counter the hallucinations, this is how the LLMs are actually evolving right now. They are increasing the number of parameters in the model so that they can understand more intrinsic, more sensitive relationships between word vector space itself, and also GPU clock speed and memory optimization, GPU optimization, clock speed optimization, memory optimization. Just a couple of years ago, the GPUs, the maximum amount of memory that can go on GPUs 3 years ago maybe was 10 gigabytes. Now the average GPU memory space is 24 gigabytes, and the clock space the clock speed on how fast they can operate has almost doubled up. So the hardware is also evolving at a faster to accommodate bigger models. And another set of evolutions is LLM architectures itself. There is there are more complex models. There are which use so multi-attention modeling, where they actually divide the tasks into chunks and distribute it among different transformer models, and concatenate them again to finally get the results. And also the training data, they're training the large language models on huge amount of data. And also there are other large language models Bloom. I don't know if you have ever heard about if you're a research community, Bloom is mostly used because it's trained on research data. So customizing the training data for large language models is one more thing. You can get large language models that are specifically designed for your use case. And serverless APIs, where the classic examples is OpenAI, where they host the high-performing large language models on their servers, and they sell them for a reasonable price. So, but do they actually address the solution? If you ask a large language model a question, can it actually give you the answer? Actually, the solution is no. The more the complex your actually problem statement is, the more it will get confused. Large language models are proven to be very accurate on smaller tasks, but they actually get confused with larger texts. That's where we use prompt engineering. Prompt engineering, and also why use prompt engineering? Because it's easy to learn and implement. You don't need to know any you don't need to have a lot of technical background, technical knowledge in the background, and all you need to know is how to get an API key, and how to connect with ChatGPT, and you can use your own prompt engineering to build well-working, efficient models for yourself. And there's a simple and effective solution, yes. And pipeline LLM thought process, which is you can actually divide your task into chunks. You can subdivide the tasks, and you can pipeline it in a way You can teach the LLM how to think, how to thought process this task, and how to finish it. You can train the LLMs on that. And the last point, regulate attention weights to address a problem of hallucinations, is that's the main thing I'm actually going to talk in this presentation, in the following slides. So types of prompt engineering techniques. Right now, there are like 3 major groups of prompt engineering techniques. These are the state of the art, mostly widely used 3 types of prompt engineering techniques. One is like a one-shot or few-shot prompt engineering, which is like you provide your prompts with examples. Like, okay, if this is a question, you answer it like this. Like how you like, this is a kind of a teaching technique that's used for kids. So the same technique is used for LLMs. And one shot is like you give one example, and few shot is like, you give more than one example. And there is another thing is chain of thought prompting, where you actually you have a machine kind of like a task system for performing your tasks. All your tasks need to follow a certain flow chart. Then you actually teach the large language model that flowchart in a chain of thought process, and the large language model follows your chain of thought prompting and just executes it. The last one is attention prompting. This is the category where RAG models fall under, but RAG models RAG models are a subset of attention prompting. And there are other kinds of attention prompting, like system to attention prompting. And in this presentation, I'm actually going to talk only about RAG and system to attention. Yes, I think that's the only 2 I'm talking about, which are mirror images of each other. RAG is where you actually provide extra data to customize the attention weights. Like if you're working with chemistry data, you don't want the LLM to confuse the carbon you're using with the carbon paper. So there you actually use you have a database of all the data you kind of deal with, and you find out the data points which are most similar to your task, and produce it as an example, produce it as an example to the LLM along with the prompts, so that it actually, you can optimize the weights of you can give a background of what's the context you're dealing with to your LLM, and that's what RAG does. But yes.
Thank you. Just a quick question, prompt engineering, is that done more on the back end when you're creating these LLMs, so the front end user experiencing the prompt that's interacting with plain language, they have a context of how the front end user will interact with it, or it's more just on the front end, me as the end user, this is me prompt engineering, just using plain language?
So prompt engineering is not on the background of the LLM. Prompt engineering is on the background of the user.
Okay.
Yes. You are the one who is using different techniques to kind of manipulate the LLM's thought process.
Yes. It's the most effective way to do it would be with just simple plain language.
It's simple plain language.
Okay.
Yes.
Thank you so much.
You're welcome. So, okay. I'm going to go show you guys the examples now. Where is it? Oh, sorry, not this one. Oh, I need to exit the slide, I guess. How to exit? No. Escape. Yeah, there we go. Okay, this is a fun, a test example I actually created to show how different prompt engineering, methods work. So, Hansel and Gretel, the classic story of Hansel and Gretel, but I actually chose this story to test the LLM, hey, this is Hansel and Gretel Chen. It's not like Hansel and Gretel from the actual story. Are you gonna get confused or not? I'm trying to test the LLM. So the background story is Hansel and Gretel, they live near Union Square, and they're going to Hex and Co, the board game plays, to participate in an AI LLM competition. And so to go to Hex and Co as a first task, they are these are the requirements of Hansel, and these are the requirements of Hansel, and these are the requirements of Gretel. They want to stop at places where all the all their requirements meet. So usually what you do in zero-shot prompting is you literally give, you're a pathfinder, just give me this is the origin and this is the destination. Just give me the path, whatever you can find. So what it does is, yes?
So question, so is, I see you have code here with said zero sys prompt. Is that the same as above in plain language? It's written code again.
The prompt itself is plain language.
Yeah, and what's the code then?
The code is Python. I'm using Python.
Oh, you're using Python.
But you can actually use it with the ChatGPT user interface.
Interesting. So you're just showing two examples to do the same thing.
Yes.
Got it. Okay.
Yes. You can use it in any language, actually.
Interesting. Okay.
Yeah. So with zero-shot prompting, it gives you it makes a best estimate of what your requirements are, and it gives you some suggestions. Hey, you can go this way, and this way. Let's see intricate details of what they actually need. So Hansel's requirements, he wants to read novels like Prince and Pauper, about young princes, and also he wants to pastel color set and chocolate cookie dough ice cream. And Gretel requirements is buy comics like One Piece. One Piece is, even though it's technically a comic, it's actually a manga from Japanese comics. And also sketch pencil set, but actually a professional sketch pencil set, not like any sketch pencil set. And also chocolate vanilla soft serve ice cream. And in zero-shot prompting, I just provided the requirements, but I did not give any examples of what they actually need. It made the best guess. But Ample Hills and so pencils, maybe yes, but bookstore, they don't actually sell mangas here. They don't sell mangas there because since we did not give any examples, it actually made its best guess. But whatever the results you get, they're not actually as good. But with examples, now it updates its results. Blick Art Materials. That's actually a really professional place where you can get professional stuff. And also bookstore, the Strand bookstore, they actually sell comics and also classic novels there, manga and classic novels there. So that's how they get updated. And chapter 3. Now, chapter 3 is finally they arrive at Hex and Co. Problem solving. So problem solving is the first round where you have they all have an LLM. They all actually trained their own LLMs, and they're peer test in the first round. They're testing the problem solving skills of your LLMs. You have to use your own prompt engineering skills to pass that round. And also second round is who am I. In this round, verbal cues are given about some characters, and you have to guess who this character is. And about me, I will discuss in that round. So first, problem solving round. So let's say you are a problem here we are testing out you're giving a prompt LLM a question and solve it. How does it solve it? So this is a question that actually is I got it from IIT JEE test. It's actually one of the world's second toughest exams for mathematics, second to Mathematics Olympiad. And in these exams, language actually matters. How mathematicians use this language is actually quite different from average daily English. So this is where LLM can get confused. If you, like if any 4 numbers are selected and they are multiplied, then probability that last digit will be like 1, 3, 5, and 9 is what? What prompt engineering, like, that's a zero-shot prompting here. With zero-shot prompting, what does it do is it came up with like a huge intricate solution. I don't want to go through the entire process, but I will show you the result. The result it actually gave is 0.5. That's not true. That's not true at all. So why is because in any set of like one so multiple, so wait, even if 4 numbers are selected, and the probability of the last digit is like multiplied, and the 4 numbers are selected, and the probability of last in any number, like you have like last 10 digits, like there are only 10 digits, like 0 to 9, 10, and out of 10, if you are selecting like 4, it's actually like 1 divided by 10, 1 divided by 10, 1 divided by 10. So it's like 4 divided by the n will be like 4 divided by 10, I think, or let me see if I am right. Yes, I think so. Wait. So I'm actually wait, am I right? Yeah, 4 divided by 10. I am right. Yes. So 4 divided by 10. The solution is actually 2 by 5. So required probability is n power 4. Like because since you are selecting like 4 numbers, for each number, it's actually the probability is 2 divided by 5. And since you're selecting like 4 numbers, it's actually like 2 divided by 5, like times 4, like power 4. So it's 16 divided by 25. That's the solution. And when you actually like this is like one-shot prompting. I mean, sorry, it's actually chain of thought prompting. Like in a solution, I'm actually giving it like an example, like this is how you can solve it. Like step 1 is this, and step 2, like you are actually explaining it like what's the probability of each number is. And in the step 3, you're actually explaining like how you have to like find the overall probability for the end solution. You are actually explaining it like how to understand the question and how to process the question. This is like chain of thought prompting is, and you actually get the final output. But another question is, let's say like there is another JEE question, like second question about probability, but this is not about like guessing the probability of numbers. It's, let's say like it's probability density function. You cannot give this same chain of thought prompting for this. It has to be different because yes, please.
So you just changed the number, right? So
Yes.
Like let's say the output or the prompt that you put in had 3 numbers, would it have figured out to only multiply by 4?
Sure, let's try it.
3, 7.
Yeah. So let's change the question. The following example is the question. Okay. 4 numbers are selected, right? Do you want 3 numbers?
Or like n number. Like would it be able to figure that out?
Yes. I will make it 3. Wait, did I make it 3? Wait, did I change it? Oh, this is the example. My bad. Sorry. I changed the example. Okay, I changed the question here. Where is the question? This is the question. Yes. Number section. Okay. Yeah, there you go. I made it 3 numbers, and also like wait. 4. Sorry. I have to change it here. So that's the question that's the real question actually. I'm providing the example with like chain of thought prompting steps first. And the final solution, yes, it did figure out.
So the chain was a four numbers still, right? Chain prompts, but then the question you asked.
The chain is like, these steps. I'm actually providing the chain here with an example because since this is mathematics, but if you are actually talking about like, how to write like, a sad story, like, a sad story has to have like, a heroine who is like living a happy life and all bad things happen. And like, like Cinderella, she actually ends up at like a poorhouse or something. So yes, please.
The main difference between zero, shot, and what is it? Thought.
This is chain of thought prompting.
Chain of thought is that in a zero shot, you give it really an example. It could be a short example, it could be a long example.
Yes, that's actually few shot prompting or one shot. Yes.
Few shot. Let's write a sad story. So you give an example of a sad story.
Yes.
But chain of thought, you're actually telling it, well, a sad story should have these characteristics. A sad story should start usually in this way. And
Yes.
this way.
Exactly. Yes. You need to give it like, steps and explain the steps. Like, you have to think this way, you have to think that way. You're giving like instructions and it will follow the instructions. So that is a chain of thought prompting. And there is another style of, like, if like the chain of thought prompting works well for a fixed use case. But if you have like, different use cases and you have a bunch of data that you are like, of examples before, then use something called auto chain of thought prompting. It's basically like, you kind of like group the solutions together. Like, these are the problems of same kind. These are the problems of same kind. Like, if the problem is similar to group one, you actually take the chain of thought prompting from group one and provide it like, oh, this is similar to this, follow these steps. And if it's similar to group two, it's similar to this, follow these prompts. That's auto chain of thought prompting. Oh, okay.
Don't you understand how you come up with this prompt? I understand there are different techniques like chain of thought and stuff, but this is all language pattern. There are n number of ways we can write the same sentence differently. So what is it like trial and error to see which particular sentence gives you the more accurate answer?
Are you talking about like how I came up with the prompt?
How you come up with this text?
This, I mean, from understanding and experimentation, like, I'll explain that to you later. Is it okay? I need to finish that. Yeah. So, and I'm going to explain the attention, attention prompting in this round. Like, okay, there are like a few guests who are at Hex & Co, like, Sherlock Holmes, how he classically dresses up with like a magnifying glass and a hat. And there's Inspector Gadget, who kind of similarly dresses up, but he has like gadgets on his head. And there's James Bond, who has gadgets on his head, but he's not detective, he's a spy. And our Homer, like, the Homer Simpson, a middle-aged guy whose name is Homer, and like, loves to play guitar, let's say that. And there is Homer 1, who is actually like, ancient Greek poet, has the same name, a middle-aged guy, likes poems, and this guy likes guitar. So let's say like, they are pretty confusing examples. And let's say like, your AI has to guess, if you're giving it clues, it has to guess like, who this person is. How can you do that? This is where like, you can use RAG. Like, okay, you already met all these guests and you made a data set of, okay, first I will show like, zero shot prompting here, example. Okay, you're a guesser, these are the clues, guess who it is. I like solving mysteries. I have gadgets in my hat. I work for secret police service. I mean, I'm not running it because we are less on time, but this is the output I get based on your clues. Could be Jack. Jack is not even at the party. Who is this Jack? This is extrinsic hallucination. Like, it's completely unrelated to our use case, context, anything. But this is too much knowledge. And how do you deal with it, there you go. Like, you can build your own RAG data set. A RAG data set usually can be hosted on like, your database server. I will not get into the details of that, but I'll give you the understanding of it. And if you feed this to the LLM and ask like, so how RAG works is like, you're actually going to have two large language models. One is to like, get like most similar example out and feed it along with the prompt. That's what's happening here. User clues and also relevant information. Inspector Gadget also has the hat and interest in solving mysteries and secret police officer and James Bond, jetpack, but a secret spy. Based on your clues provided, the answer is Inspector Gadget. So that's how you deal with like extrinsic hallucinations. And in this one, about me, like, in this one, like, the participant itself, like the final round, there are only a few participants left and they're competing with each other. So you need to provide like, a confusing story to your opponent, and your opponent LLM needs to guess like, some facts about like, is this actually related? Is this actually about you or not? Is this question like, let's say like, okay, Hansel and Gretel, this is actually Hansel and Gretel Chen, not real Hansel and Gretel. You can see it. And also I provided it in the LLM actually. Okay, this is not the story, by the way. So this is the story. Damn it. I need to update that. But what's happening here is, so basically the LLM so basically I actually like, took the original story of Hansel and Gretel and actually changed like, few details of it, and like, added like Hansel and Gretel Chen there, and like, in Long Lost, they actually lived in a damp little cottage in Long Lost toward Germany. And so okay, this one is actually like Hansel and Gretel actually are participating in a play. This is a 6th Avenue Elementary School in Manhattan, and they are playing as like, real Hansel and Gretel. That's the original story of Hansel and Gretel. And if you actually read this as a human being, you will know like where does Hansel and Gretel Chen live based on your understanding. They live in Manhattan. They're not actual Hansel and Gretel. But LLM with zero-shot prompting, it actually gets confused. And the question I provided is, you're an information extractor. Wait, sorry. Yeah, zero-shot prompting is here. Okay. What did I question? Yes. Where does Hansel Chen and Gretel Chen live? In this text, there is no direct evidence that where Hansel and Gretel Chen live, because they could live in like, New Jersey and probably going to that school, or maybe not. But the zero-shot prompting actually gave this answer: damp little cottage on a dark side of Long Lost Wood in Germany, which is actually where they live in the original story. So this is intrinsic hallucination. Sorry. So to deal with this, we actually do something called system to attention prompting. Humans actually have like a system to thought process and system one thought process. System one is like, unconditional thinking, how like, like cerebral cortex actually like, makes you do like involuntary actions. And system two is like, you use reasoning. And here we use reasoning. We actually like, make the LLM summarize like, all the points of the input text what is provided, and like, get rid of all the unwanted text. Take only text that's actually relevant, and now make the inference, like, if there is information provided on Hansel and Gretel. Like here, actually ask the LLM to provide the, like, get the summary of it. And I'm give another task, like, this is a summary, extract the relevant information to this question. And the relevant information is this: Hansel Chen actually played as, they're the characters. They're actually the actors who played as these characters, and they go to this school. And there you go, like, that's actually system to attention, like system to thought process. And what's the final answer when you ask the question using the extracted information? Not enough information provided. That's the right answer there. So this is the system to I know most of the companies are actually using RAG as a basic solution for dealing with majority of the plasmas. Use more RAG, use more RAG, use more RAG. But there is also other ways of dealing with hallucinations. They're not just one type of hallucinations. There are many types of hallucinations. So that's what I wanted. And I will end my presentation here.
Thank you for that.
Thank you.